Yeah, exactly. Lots of typing to do here. All right, let's go ahead and start. Welcome to week 13, and this is episode 23. So the to do this week, we do have PAA doing. All right, so I see that many of you have already started working on it. Good progress. And this week we again have 4 quizzes from 34 to 37. Okay, they are also due on Saturday. And yeah, many of you might have already received emails from Google Form informing you of your grades. And you can also see the distribution of the grades by clicking into Channel Exam 2. Okay. And this time that you see the grades are substantially higher because Poly has made it more relaxing and a little bit lighter for you guys to work on. So we do have students getting grades in the 90s range. Okay. But generally, we still have like a bell-shaped form. Most of you guys are in the range of mid-70s. Okay. All right, so that's just so you know how you did among the classmates. Okay. But I do like that many of you have progressed. Okay, you are doing much better than exam 1. Now, of course, the numerical numbers is usually higher, but I do see that many of you actually study more. Okay, there are, however, a couple of you. I can tell that I think the second part of chapter 3, you will have trouble juggling probably among many courses you're taking. Okay, so I see that you guys did well the first half of the exam and then falling short the second part. Okay, so that's assessment of the exams, and I see Zong Huan and Jiawen coming. Welcome. And we do have 3 topics today. So the first topic is to actually follow up on the last topic we talked about last week. We introduces this thing called IP address. And IP address does have like a structure where we have the first few bits being the network address. And we also call this the prefix, okay, the address prefix or network address. And then the last few bits, the host part, okay, the host address, okay, of the IP address. So within a subnet, okay, within an local area network, many of the machines will share the network part of the address. But each of the machines will be able to tell apart by others by looking at the host part of the IP address. Okay, so in the end, the IP address for each machine is still unique. And yet you have like this last name and family name separation, right? We can tell you're from the same subnet, much like your last name tells people many of you are from the same family. All right, so we do have this hierarchical structure in IP address, right? Higher level, the network address. Lower level, the host address. And we talk about the benefit of doing such an hierarchical addressing, right? For routers, we use prefix to do lookup, right? And we use prefix to make sure that the forwarding table is what? Compact. So those are the benefits. And last week, we ended up saying that there's one more benefit with such a hierarchical addressing mechanism. That is also to save amount of advertisements we need to send to enable routing. Okay, but you see that we have not yet talked about routing because routing is in chapter 5. So this video coming up is probably trying to give you like a crash course, right, within 4 or 5 minutes, what routing is like. The goal of routing is to form these forwarding tables, if you recall, right? Destination IP and outgoing interface. Now, the way these entries are formed is this. If this is a destination, if somebody else on the internet wants to send data to this guy, this guy will need to announce its IP address, okay, in an advertisement and travel through the network like this to outside. Okay, that is how the router here discovered, oh, okay, I see a destination potentially this way. So that IP here, and yeah, the outgoing interface is this guy here. Now for a guy, okay, who's connected to the internet this way, that advertisement will go down, yeah, this other interface. So this other guy here, IP prime, yeah, the output interface will be linked here. So that is the general idea of routing. But then you see, for each machine here having an IP address, in order to allow other people sending packets to it, they would each need to send an advertisement announcing its IP address. Okay? And there are these many different IP addresses possible, so potentially worst case, right? Lots of advertisements each of these organizations need to send and travel on these links. And you know what? The most scary thing is this. All these need to go out to the internet, so the ISP needs to send these many advertisements. And that is just not going to scale. Okay, that will be a lot of bandwidth consumption just to send the advertisements. The solution is actually related to the forwarding mechanism in the router. If you recall, instead of listing individual destination IP here, rather we do this, individual prefix, okay, and then outgoing interface. So when a packet arrives, the destination IP address matching the prefix, then we send it out on the outgoing interface. You know what? Isn't this a prefix? Isn't this a prefix? So what we're doing, in fact, in the internet is not to send individual IP address in the advertisement. We send an individual prefix in the advertisement. So what's happening there is the prefix in the advertisement gets here. Router here, receiving it, pass it down further. Router here, receiving it, pass it down further, but also add the entry prefix here. And because it's coming this way, so this OIF is going to point to this interface. So when a packet arrives here, matching the prefix, go on this interface, and coming here, this router is going to forward it, similarly, down this way. And then coming into the organization 0. So by announcing or advertising the prefix, right, we also draw the data into the organization. And the data is actually destined for one of the hosts in the subnet anyway. So the routers inside the subnet there, which is, we'll be doing further routing there to get to the final destination. Nice. So you see, instead, organization 0, 1, 2, all the way to 7 will be sending one advertisement only instead of these many advertisements. What's even nicer is this, the ISP. Yeah, ISP doesn't need to send 8 individual advertisements out, just send one. Because it's very easy to aggregate all these, right? Because this is the coarser granularity covering, right? Superset of all these subnets prefix. So there's just one advertisement out this way. One on the link, one on this link, one on this link. Advertisements, the distribution of it, very, very efficient. And so here, the entry is simply 200 something something 6.0, and it goes on this interface. Data matching this will all fit and then go on here. This router here that will split the packet 8 ways, and by checking the destination address of the packet to these 8 different prefixes and see which prefix match better. So that is the idea, and why we say more bandwidth here. This is the third benefit of doing the prefix matching, in addition to what? Making the forwarding table smaller and the lookup process faster. All right. Now next, there's a very interesting case. You see that, hey, such an hierarchical addressing will still work with the subnets shifting around from one ISP to another ISP. Here's the video. So the slide here is actually introducing a very interesting scenario. Okay. organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the two of them are not aggregatable. In this case, two separate advertisements will go on out into the internet. The forwarding table here will contain two entries. One is starting with 199 and one starts 200 dot something 18.0 and 23 bits. This one is 16 bits. And of course, this entry here, okay, will arrive also at the router here at the internet, on the internet. And therefore you have 200 dot something, 16 and 20 here. So this entry is gonna take the packet out this interface. These two entries is gonna take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's gonna match the first entry, isn't it? It's not gonna match the entry number 3 because hey, this address space and this address space, they are actually disjoint. Okay? So not gonna match this guy here. So packet going for destination organization 0 is gonna go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay? As long as the destination IP address is matching this, it's gonna come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's gonna match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right? Hey, it's gonna also match entry number 3. Now, if we call back in section 4.2, what did we say? We're actually not just doing prefix matching, we are doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So ICANN here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about ICANN. All right, so what do you know? The IP address, the structure is actually cool. Okay, works really nice. Now we switch gear a little bit and talk about the next topic called NAT. And this is a service, again, at the application level, but it's so commonly used and it's addressing more a network layer issue. Okay, let's hear the introduction. NAT, the Network Address Translation Service. This is one of the most used protocol on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32, it sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this: you pay a specific amount of money monthly, you get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get 1 static IP address or 4 dynamic ones. Okay? If you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay? We just, subscribe for 1 IP address. And then we create a home network, okay, using some fake IP addresses that we make up, and subnet address that we make up. So instead of asking the ISP, okay, asking the system admin for a block of IP addresses, we can afford it. We use fake, block of IP addresses. So we call this local network or home network. Each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we are sending data within ourselves, it should be fine. But if we want to send data out, wow, we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped, at the ISP. So if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, each of these connections to not collide to each other will be assigned a new port number as well here, a different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of NAT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this: we don't need to ask the ISP for a block of IP addresses, which is very expensive. 1 is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. 1 is this: if we want to change the IP address in the local network, we just change it. It's not like, we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay? But if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. We just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is 138 something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. So subnet or virtual address or fake IP addresses are not addressable. By not addressable is what I meant is packets coming from originated from outside just have no way of reaching. So yeah, so they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, unexpectedly. All right, so nice to have an AT. Now let's talk about the mechanism in more detail. Net's mechanism is quite straightforward. Only 3 steps. 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local net to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with the new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these 2 values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in Net's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote hosts receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet's coming into the local net. The net box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate, it will be easier to understand. So the local net here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the net box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the net box here. Step 2, the net router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay. So destination port, the source port number of the request. Now, this packet will come back to the net box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number, and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address, because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN site address. Okay, port number also with the LAN site port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how net works. All right. And now the next video is a little bit long. It's to talk about what's not so good about using NAT. In fact, NAT is a little bit controversial. And right after this video, quiz 34 is coming up. Last are the drawbacks of NAT. Point number 1, port number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number 2. Yeah, NAT is controversial. In the previous slides, you might see the authors of the textbook referring to these NAT devices as NAT routers. But routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NAT, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number and the port number fields in the packet header. IP address. Yeah, that is a field in the, I know, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header. It's in the layer 4 header. So NAT as a router should not be doing that. So those who are against NAT boxes to address the network shortage, IP address shortage problem, okay, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NAT box. Yeah, hosts sitting behind NAT box cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Okay, not even reaching the NAT box in the middle, the IP address being 138 or something. Right? Only packets with the destination address 138 or something will be able to reach NAT box. Okay? And NAT box there, it will also not know, right, what port number, what local IP address to convert back to reach 10.0.0.1. So, yeah, it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, the box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router, and the NAT box, look up the table and then translate back. So originated from inside, no problem. But data originated from outside,
big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we will try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the net box, sitting behind the net router. So we'll have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice will need to call a relay peer, and the relay peer will exchange packets for each other, okay, for these two peers, for Alice and Bob. So application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is going to break. Okay? Unexpected might happen. So one layer's protocol designer needs to worry about another layer's, how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this. The reference protocol stack there, okay, application, transport, network layer. So we say nice about building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to.
All right, good. So now you know that NAT is a little bit controversial. Some people actually consider using NAT as a bad thing. So quiz 34 here is to actually push you to think a little bit more critical. Whether you are supportive of using NAT or disapprove of using NAT. So this is quiz 34, ideal versus practical. One can be very idealistic, but usually the suggestions or solutions might not be exactly practical, and vice versa. So Q1 is asking, straightforward. Would you rather pay for multiple global IP addresses from home access, or just use NAT and get one IP address instead? Okay. Now, if you prefer one, why? If you prefer two, why? Q2, would you prefer using NAT or okay, so I see a question popping up, but let me finish the quiz and then we can come back to Inti's question. Q2 is asking, would you prefer using NAT, or IPv6? Although we have not yet talked about IPv6 in detail, but generally in IPv6, we have 128 bits IP address. So that's 2 to the power of 128 different IP addresses. That's much bigger than 2 to the power of 32. Okay, with IPv6, think of it this way. Potentially the cost of getting an IP address is lower. The cost of getting an IPv6 address is lower. Okay. Now, so comparing IPv6 to NAT, which one would you prefer? Okay, and why? All right, so that's let me allocate some time to the quiz, and guys, work on it. With regards to Yunqi's question, maybe I can just type up first on the chat, okay, while you guys are working on the quiz. Good 34 turned out to be quite challenging for you guys, right? Because obviously you need to think, hey, which one you prefer better. And it's very subjective. There's no standard answer here. Okay. So let's see. Team 4 already type up something. Let's see what Team 4 says. Wayo prefers using net because it can save money, of course. Okay. Oh, poor you guys. Being student, right? You're always short of money. Yeah. Okay. This is very insightful, but I actually agree with you. Wayo is thinking that cost is one of the major factors before you decide buying something. Okay, so cost, the price, is one major factor for the consumers to decide whether to buy or not. Okay. So okay, let me come back to Team 4, Q2. All right, and Team 4 is saying they would prefer IPv6, although it contains more bits, but it can solve the problem that NAT will encounter. I see. I guess Team 4 is paying attention because I think Yunqi was asking, right? Why NAT is so bad in terms of breaking the modularity in the layered protocol stack. Again, as I mentioned, right, for people designing a P2P protocol, if we don't know, right, there's NAT, and with NAT there, then you cannot set up direct connection because my IP address is 10.0.0.1. Your IP address is probably 192.168.something. Both of our IP addresses are fake ones. So that means on these routers on the internet, our IP addresses, routing entries are actually not there. So there might be a machine on the internet with the IP address 192.168.something. But that machine is not the other peer that is using 192.168 behind that. Okay. There might be a machine with IP address 10.0.0.1 on the internet, but my 10.0.0.1 is actually a fake IP. So if someone sends packets to 10.0.0.1, it's going to go to the real host owning the IP, not me. Yeah, I guess Jiawen was asking the same thing, asking something like this, right? Which IP address see in common situation? Net IP address or source IP address? Yeah. So you see that if I am the data source, okay, when I send packets out, I'll be using my IP address. But the thing is that if I am behind NAT, when I join the local network, I ask the DHCP server for an IP address, and the local area network here using the fake IP address is going to assign me a fake IP address. Therefore, all the packets that I send out, Jiawen, will be carrying a fake IP, the IP given by the netbox. So that will be in the source IP address of the packet I send, I'm using a NAT IP. So the receiver of the packet, okay, if it's in the application space, we'll see my source IP. Okay, but of course that packet, after going out through the netbox, is going to be translated to the real IP address the subnet is allocated. Okay, so that the server is going to respond. If this is going to a web server and then send back somehow, because there's because after the netbox, the source IP address is translated to the global IP. Okay, so that packet can travel the internet. Okay, but the receiver there, okay, if it's HTTP, it's going to send a reply with the destination address being the netbox's global IP, okay, and translate back. So if you initiate me as source behind net, send the packet out, people can respond. So other servers can respond. But you see, the machine that I'm connecting to is a web server. Web server has a global IP address, so I can reach a web server. Web server can send a web response back. But if this is P2P application, so me, for example, if I try to connect to you, Jiawen, and you are now in the dorm, and you are also using NAT, not the global IP. You are not a web server. I don't know your global IP. I mean, what do I do? Where do I send? Well, for P2P application, we might be able to do this, right? Check our machine and then get each of our IP address, but these IP addresses are fake. So we can try to send a message to the directory service of Skype, and then we find out the IP address of each other. But both of these IP addresses are fake ones. We can send packets out, but it's not going to reach any one of us. We are going to reach each other. Jiawen. Okay. Now, I don't know what kind of IP address. I mean, if we receive packets from outside, the source IP address usually is the global IP. Okay. So just like when I'm in behind net, when I send a packet, originally a source IP address is my fake IP, but after the net box, it's going to be real IP. Okay. But when we are sending packets and we are behind net, oftentimes the initial packets source IP addresses are fake. But when we're receiving them, the source IP addresses are usually real. And to receive them, the destination IP address needs to be also the real one, okay, that can reach us. Yeah, the P2P applications, it really depends on whether the P2P applications knows that the users are going to be behind net or not. Otherwise, the P2P applications won't know, right? The IP addresses reported by the peers, are they real or fake? And suppose the application layer protocols, they don't need to know, right, whether there's NAT, whether you're using Wi-Fi to connect to the internet, whether you are behind NAT, whether you are connected to a Cisco router. So applications, they should only say, hey, and this application requires reliable connection, so I want to set up a TCP connection, right? Because the next layer is transport layer. Network layer, link layer, way off, too far off. Yeah, so the reason that Skype set up something like a super peer node to try to relay calls for peers behind that is because P2P, so Skype designers, they know, nowadays lots of users are really behind net. So the designers need to know something extra. So that's breaking the end-to-end argument, because NAT is a network layer toolbox. Okay. I think Chunmao, is it possible for us to build a server acting as NAT in local? You know what? It's possible. And receiving data from local hosts and pass it outside, so it will not violate the end-to-end argument. It will still be a little bit hard to not break the end-to-end argument because yeah, I think Chunmao, you are asking a very, very good question, because there are other protocols designed exactly to provide the kind of service you are thinking. It's called the net traversal plug and play. So it's possible that on the host, okay, behind NAT, as well as the NET box, the two of them try to communicate. So the server can discover, so the host can discover what is the global IP address. So therefore, at the application level, okay, if this host join a P2P service, can report to the P2P's directory server saying that, hey, this is the global IP address, instead of naively reporting the IP address configured to the network interface. Okay, so Chunmao, very good. But we don't have time to talk about NAT traversal, to talk about net traversal, but we do have a video. It's on the same channel that you are attending to the lecture. So there is a video called NAT net traversal. Click into that video, you will see that how we get around this issue. Okay, and so that we can try to talk at the application level or transport level a little bit more transparently. Okay. All right, hey, let's come back to the quiz 34. Good, I see you guys finishing discussion, debating maybe among yourselves. So team 1 prefers 2. I think this is paying more, right? Wow, okay. Let me see. Oh, okay, so wait, no. Team 1 is suggesting to use NAT. I think this is cheaper. Okay, same reason. And for Q2, IPv6. Yeah, so we don't have the problem that we need to try to traverse through NAT. Okay, so guys, if you don't need to set up servers, using NAT, no problem. If you don't need to use P2P applications, naive P2P applications, no problem. But if you want to set up servers, or if you want to use more naive P2P services, then you need to think about, okay, NAT traversal, or better yet, use IPv6, where you get multiple IP addresses and cheaper. So Yan-Yo is going for IPv6. Team 12, the preference seems to be NAT, because since I have multiple devices that you need to connect to the internet, and you probably don't want to pay all that many IP addresses, right? I think NAT is a method that have to reprocess data. Oh, okay. Bing Rui has a very good point, because the netbox there needing to do translation. It's going to take some time, so add to the delay. I see. That's why you stick to IPv6. So you're not quite thinking about needing to traverse through netbox. All right, team 2, using netbox, cheaper. IPv6 prefer. Then all then will not work. Yeah, if both sides are behind NAT, right, it will not work. NAT, cheaper, good. So for Q1, the answer seems to be quite consistent. For Q2, yeah, I think you guys prefer IPv6 as well, because then we don't have the controversies. Poor. Application designer. Yeah, okay, so Min Hong is thinking from a designer's point of view. If you guys would design something like BitTorrent, then you could make the mechanism simple and make it faster, easier to implement and push to the market. So IPv6 will be something that definitely network engineers or application layer protocol designers like to have. The extra security is also beneficial. Okay. Oh, wait. Oh, you meant something different here. You want to use NAT. I don't have to worry about how to implement. Okay, so I'm actually not quite sure if I understand this part. The scale of the application is huge. Consider net because it's less cost. I see. Yeah, I think for Q2, Team 14, Ming Hong, is suggesting using net. That is probably because if we have many machines that we need to connect, then we need many IPv6 IP addresses. Okay, so they might add up to be expensive again, I guess. NAT because it's cheaper and safer. IPv6, we get more IP addresses and cheaper, and you don't have to worry about traversing through NAT. NAT, IPv6, good. So about setting up server, just quickly before you go, about setting up servers, many of you probably don't do that, but think in the future. I think I'm creating enough video content now. Instead of using Dropbox or Google Drive, I find the space is not going to be sufficient. So I try to set up my own pollys Dropbox in my home network. And so I do need to handle the net traversal problem there. Okay. And that's going to cut down the cost of subscribing to Dropbox, subscribing to Google Drive. And yet I just, add more disk space there. Okay. That's called the NAS, the Network Storage Systems. NAS, I think. Network Storage System. Think about in the future that you guys might need to set up something like that in the home network. All right. So I think this is good discussion already. I hope that spending a little bit more time here helps you understand exactly how net works. I understand that there might be some notion that is still a little bit confusing. Take some time and review what we talked about. If there are questions, feel free to post on Slack, ask us anything. Okay? Or tomorrow, tune in again. We'll continue. And the next topic is IPv6. With that said, I say goodbye. I see you tomorrow. All right, I think some questions depends on our network usage. If we own servers that need to receive requests, yes. However, for personal use, that is enough. Okay, good. All right. So I guess Team 5 is selecting NAT for both cases. I guess in Youxiang's case, there are no servers, so strictly NAT. It's gonna be cheap all the way. Okay, bye, Yanjun. The server doesn't. Do you mean the HTTP server or the server behind that? So what happened is this. So I'm actually assuming you are talking about the example we just talked about, right? There's an example, a host 10.0.0.1. Yeah, good, got it. The server will know that port number because the HTTP request message, right, will carry the netbox's IP address, and the destination, the source IP address will be netbox's IP address, and the source port number will be the port number that the netbox assigned. So in that HTTP request message to the web server, the source IP, source port number are already given by the netbox. Now the server sends back a response. In the response, the destination IP and destination port number will be simply the source IP, source port number of the request. So the web server knows how to send the message back to the netbox, and therefore netbox can translate back to the local host. But I think, Yunqi, you are thinking, hey, that seems to be working, NAT, working really well. But NAT works well when the communication is initiated from the local host and back. So we were actually talking about net traversal because sometimes you do have need to set up a server inside the local network behind netbox. So think about if you want to set up a NAS server, okay, where you store all your homework, video, your MP3 files, your life's work, because there's just not enough space. And Dropbox, Google Drive getting expensive because they begin to charge people and charging more and more. So it seems that a better solution, more affordable solution, is to set up a NAS at home. But if your home network is behind NAT, you won't be able to access your NAS anytime, anywhere. You could try to set up a connection to reach your NAS, but NAS is assigned a 10.0.02 IP address. Okay, and you try to connect to 10.0.0.2, but that packet is going to go randomly on the internet somewhere else. Yes, there you go. Yeah, if you want to set up a server and you'll be waiting for people to connect to you instead of trying to connect to someone first. Exactly. I think Yanjun got it right. It's okay. I think Jiawen and I think a few of you guys also was a little bit confused. And Yanjun was very observant, right? That example I showed, net is working well because the guys behind the net initiates communication, then no problem. But if you have servers behind, server always wait for people to come contacting them, right? So if you want to access a server behind net, then you have a problem. All right, good. Good that we're able to figure this out. But I hope that I did not delay you from going to the next lecture, Inchi. Alright, and it's good timing, so let's end the stream now. I see you tomorrow. Cheers!